So again, looking at radioactivity, and unbeknownst to Lord Kelvin, was in 1895, Henri Becquerel, a French physicist, discovered this radioactivity, and he had two graduate students, Pierre and Marie Curie, who really figured out how this radioactivity works and explains Earth's internal heat production, provides a powerful tool for dating geologic events very accurately. And what's more, you'll find that there are several atomic clocks that are keeping time at their different rates of decay, but they're keeping track of that same event in the geologic past. So in other words, we can use several isotopic systems or atomic clocks, and they all are giving us the same age for that sample. Now, we talked about atoms and elements and isotopes when I talked about minerals. One of the key things I want to point out here is that we have the chemical symbol, in this case uranium, and by convention the superscript here, 238, refers to the atomic mass. You can think of this atomic mass as also the isotope, because you can see uranium has uranium-238, uranium-235, and uranium-234. All three of these are isotopes of uranium. Remember, iso means the same, tope is type. That's because this number here is all the same, 92. And 92 refers to the atomic number. And the atomic number are the number of protons in the nucleus. What's more, it defines the atom. Remember, the atomic mass, or the isotope number up here, is a number of protons plus the number of neutrons. When we look at isotopes, they're going to decay. And your book talks about these three forms of radioactive decay. There's alpha decay, there's beta decay, and then there's something called electron capture. But all three of these are important because the isotopes that we use in geology will decay according to one of these three types of decay. So let's look at this first one. The key thing about the alpha decay is we're changing the atomic mass by 4 because we're losing 4 particles, right? So the atomic mass changes by 4, and then 2 of those particles are protons, so the atomic number decreases by 2. So in this case, if we had uranium-238, this uranium-238, which has atomic number 92, decays by this alpha decay, so it's kind of a symbol like that, which means that we're going to have a change in mass of 4, so it's going to be 234. So the resulting isotope will be 234, and its atomic mass will be 90, right? Because we're losing 4 particles, two neutrons and 2 protons, right? So that's -4 there, and then 2 protons, which decreases the atomic number from 92 to 90. And that element is thorium, right? So we get 234 thorium. And so that's one decay that we get from this alpha decay. But you'll see that the uranium decay series, uranium eventually decays to the stable daughter product of lead, but it does it in this decay chain where it goes several steps. The next step after thorium-234 is actually a beta decay. So if we take this thorium-234 and we undergo a beta decay, well, the beta decay, what's going to happen here is if we look over here, we see that we're going to lose a beta particle, which is essentially an electron, from the nucleus of the atom. So remember, in the nucleus, we're going to shoot out an electron here. We're going to lose an electron, which means in the nucleus of those atoms, remember, there's protons. We'll make a proton there, but there's also neutrons. Remember, neutrons have both positive and negative particles. And so in other words, that electron is lost, which converts the neutron to a proton. So basically, we're gonna have a neutron converts to proton. Neutron converts to proton. We're not going to change the mass, right? Because we're not losing any protons or neutrons, but since that neutron now becomes a proton, we have to increase the atomic number by 1. So that's what this is saying here. So what does this become? So if we look over here, we're going to have the same mass, 234. But now we need to increase the atomic number by 1. So we're going to have something that's 91. And that's palladium-234. And then you can see that this will undergo another alpha decay. And so you'll see a whole series of steps. In fact, the next slide I have here shows that step decay series for uranium, right? So here we go. Uranium-238 undergoes alpha decay to thorium-234. Then there's 2 beta decays, actually, to palladium-234. That's what we had over here, right? Palladium-234. which is atomic number 91. You can see it right here, 91. And then we'll see another beta decay to uranium-234, but then we see another alpha decay here. And later on, you'll see that this uranium-234 to thorium-230 decay, we actually use it for dating carbonates, calcium carbonate or calcite, especially in marine environments, because uranium-234 can dissolve in liquid pretty easily. And that has a half-life of 75,000 years. But we'll come back to that. Now, the last type of decay is this, in fact, we call it a positron or electron capture. So in this case, an electron makes it into the nucleus of the parent atom. So in this case, we're not adding or taking protons away, so we're going to leave the atomic number the same. But what happens since we add an electron to the nucleus, it's going to be really the opposite of beta decay. We're adding an electron in here, so we're going to convert a proton to a neutron. So let's write that down over here. So we'll look over here and we'll look at this electron capture. So what's going to happen, we're going to add an electron to the nucleus of potassium-40. And potassium-40 is one of the isotopes we'll use for especially dating volcanic rocks. So when we do that, remember in this case, we're going to not change the atomic mass down here, but we're going to change the atomic number. We're going to decrease it by 1, because what's going to happen here, we're going to convert a proton. So proton is going to be converted to a neutron, which is both positive and negative at the same time. And so in that case, we're going to get something that's atomic mass 40, but has atomic number of 18. And you'll see that that element is argon. So the potassium-argon method of dating is one that we use quite a bit for volcanic rocks. So again, those are examples for alpha decay, beta decay, and then this electron capture or positron. So again, this is showing that decay series. The final product of the uranium decay series is going to be lead. So in this case, lead is stable, and that's an end product of this radioactive decay. But you can see there are several steps that are involved in this decay series. So here we have uniform decay. The way the radiometric systems work or decay work is that we start off with a given number of parent atoms. And the key thing, there are no daughter atoms, because the parent eventually decays to a daughter. For example, here potassium would be the parent, argon-40 over here would be the daughter. But at the time of crystallization, when the system first closes, so in other words, we have a magma, there's potassium, and even maybe some argon in the magma, but only the potassium gets crystallized into the mineral. And so now there's no daughter product, and we have 100% parent atoms. And you'll see that after one half-life, that number is decreased by 50%. After two half-lives, we'll be down to 25%. So we'll be half of that 50. 3 half-lives will be half of 25, which would be 12 and a half. 4 half-lives will be half of 12 and a half, which would be 6.25. And you can see that this decay, we start seeing that it starts dropping pretty quickly here. And then as we start having fewer and fewer parent atoms, it starts approaching the x-axis. So it really becomes like a tangent. And this type of decay we call exponential decay. Let's look at this little game that is put in the lab, and I downloaded it in the lab, and I don't know if you can get it on there. I had to work to get it on there. I had to go to the website and put it on there, but I can show you what you can do with this. So actually, in this demonstration, I'm going to show you carbon-14, and carbon-14 has a half-life of about 5,730 years, 5,730 years. And you'll find that we're going to have a lot of carbon-14 atoms, a lot of parent atoms to begin with, but then you'll see that there's a random decay, but you'll see that most of them will start decaying pretty quickly, and then as we start having fewer and fewer parent atoms, we're going to see a slower decay. So let's start this here, and we'll reset them. You can see there's a bunch of decay here, but now it's starting to get spread out, and there's less and less. So that's just showing us that there must be some rate of decay, and that rate of decay, so if we reset all these nuclei, you can see that the parent is decreasing, but the daughter is growing. And again, we're going to approach the x-axis here tangentially. Now going back to our slides here. So the way this numerical dating or isotopic dating First, you determine the half-life of the sample. Then we measure the parent and daughter ratio using something called a mass spectrometer, and I'll show you a picture of that right now. And then we calculate the age of the sample that contains a radioactive element based on the half-life of that sample. And I'll give you some examples here in a moment. So here's a mass spectrometer. So we take our sample, our uranium or our lead, and we load it onto a filament inside this vacuum chamber. And in fact, this whole thing is under a very intense vacuum, so that when we shoot those atoms, those isotopes through this magnet, they're not going to hit any air particles. So we want to have a vacuum in there. And what's more is when we ionize or start sending the atoms down this flight tube, they're going to bend. They're going to be bent by the magnet depending on their mass. In fact, this next slide shows we ionize, and you can see the lighter masses, in this case mass 44, gets bent more than the heavier masses, which is mass 46. And then we put these little Faraday cups, which essentially they can sense. They're like voltage meters. They can sense when energy hits them. Essentially what they're doing, they're counting atoms, they're counting isotopes. And then it goes to an output, and we read it on a computer. We can read how many atoms are coming out, right, on this mass spectrometer. So now we'll continue with some of the problems that may occur in terms of obtaining an accurate isotopic age. In this slide, we're going to show a magma. Note that here we have a liquid, and these are the atoms. And in this case, we have radioactive parent atoms, and we have stable daughter atoms, all mixed in there. They're all in the magma. And as the magma cools, crystals begin to form. In this case, it looks like these are zircon crystals. One thing that zircon will prefer uranium over lead. So if there's any lead, usually it will not go into the uranium crystal. And so only parent atoms go into this uranium crystal. But once the magma cools below this temperature called the blocking temperature or closure temperature, then we've closed the atomic clock. And now here the whole magma has crystallized, and some time has passed in this igneous rock where some of those parent atoms have decayed to daughter atoms. So note that at the beginning of the time when the isotopic clock closed, or this blocking temperature, there were no daughter atoms in the crystal. But after some time, some of these parent atoms started to decay and turned into daughter atoms. So in this numerical dating, if metamorphism occurs, if this rock is heated up to a high enough temperature above that blocking temperature, that may allow some of the daughter product to escape, which means we will not get an accurate age. We'll get an age actually younger because we've lost this daughter product than the true age of the rock. So metamorphism can give us ages that are incorrect. Now, what are some of the atomic clocks we're using? In geology, we're primarily using the uranium-238, which decays the stable lead-206, and it's going to have a half-life of 4.5 billion years. Then there's 235, which decays the lead-207, and that has a half-life of 704 million years. And also there's a thorium-lead, and then rubidium-strontium, and then I've talked about the potassium-argon, and that has a half-life of about 1.3 billion years. We talked about potassium-argon, but we didn't talk about the argon-argon dating method. So argon-argon is similar to potassium-argon. In this case, we're using that to date volcanic rocks anywhere from 2,000 to 4.6 billion years. One of the problems with the argon-argon system is that these are both gases, so we can get some loss of either parent or daughter product there. Samarium neodymium, this is more of a system used for determining whether lavas have a stronger component of the mantle. And then uranium thorium, we talked about this one, how it has a half-life of about 75,000 years, and it's used for young samples of calcite, and it's reliable back to about 500,000 years. And then your book also mentions this method of fission track dating, especially in crystals like apatite. When the uranium decays, it's an alpha particle, it's a very large particle, and it can leave these tracks, or this radioactive decay tracks in the crystal structure. And the only way to see that is if you etch the crystal in hydrofluoric acid, which will bring out these fission tracks. And the key thing is you can count these fission tracks, and knowing the amount of uranium you have in your sample, you can estimate the age of the sample.